denominations. Okay, so you have denominations d1, d2 up to dk cents, and you have an amount x. And you want to find the best way, and here I define best as the fewest distinct coins, to hand out x cents using the given coin, okay, the given coin denominations. Okay, so let's see an example of this. So suppose I have these kind of coin denominations. I have just 4 of them. So k is 4 here. There's 1, 5, 10, 25. And I want to make let's say 55 cents out. Okay, and suppose x is 55 cents. Okay. So the question is, how many coins do we need? How many distinct coins? How many coins do we need? So what's the answer here? 3. 3. And how did you guys come up with it? Yeah, so this is what people always do, right? So if you go to a shop, this is what they do. So if you have, so you start off with the largest one, give as many of those as possible, and try to give change for the remainder. So this is, in this case, the right answer is also 3. Necessary and sufficient. So in this case, why are 3 necessary?
Because nothing is necessary.
Yes, so yeah, so in this case 2 is obviously not possible. Okay, so 3 is necessary. So this is an easy case. So you have something like this and do it. Okay, so in general you could have an algorithm like this, right? So you could have an algorithm that says so you say that basically choose coin of highest denomination that is smaller than x. Okay, so this is what you guys are saying. Okay, so highest denomination smaller than x. Okay, include it in the solution and keep going. And recurs with x minus that, let's call this something. Let's call it d prime or something, x minus d. Okay. So any questions on the algorithm? This is the first thing you would think of when you see this problem, right? So if I have a bunch of coins, to make 55 cents, you'll say, okay, let's give 55 is pretty big, so let me start at the highest denomination, give them out, and then I recurse. So, okay, so this is fine. So can you guys come up with a dynamic programming solution? I mean, just for the heck of it. Yeah.
You can come up with every combination and then store the values, and then when you see a value, if that's equal to just return something.
Yeah, so something along those lines, right? So I'm not going to go into this in detail because we've seen more intricate examples of dynamic programming, but you can always say I store an array which maintains the best possible solution up to x. Okay, so store an array says best solution for n going from 1 through or 0 through capital N or capital X. So you can have an array like this of size x. Okay. So for every integer you store what is the best number of things you can have, okay, or the minimum number of coins you need to make that integer. And this you can update using dynamic programming. I mean, you can update using the recursive rule that best of n is min over the I of n minus di. So this is if you chose to give out one coin of di, and then you've got to add 1 because you've given out one more coin. Okay, remember that you're measuring the number of coins you're giving out. Okay, so 1 is the number of coins you've given out, and best of n minus di is this. So it's min over I because you could have chosen any di that you want to do. Okay. And if you stored these values, then you can just look them up, and then you can compute best of n using only values of best of n for n less than this. Okay. So yeah. So anyone not clear with this algorithm? This is a very standard dynamic program you can write for this. So maybe think about it for a minute. Alright, but this takes time which is significantly larger, right? Because for every n you're actually making some k different lookups like this, and you also have an array. And you want to make change for, I don't know, 500 cents. Okay. Then it's pointless to store a full array of size 500 and compute it for everything. So I guess you realize that this is actually kind of pointless. Okay, so any questions on why dynamic programming doesn't sound really right for this problem? Yeah.
Because we not necessarily we go through every step of while recursing down. So if x is 500, we definitely don't need all 500 of those.
Yeah. So that's something we'll see in our homework. Basically, keep a sliding window. Okay, so so you don't have to like really keep large numbers. So yeah, we'll see something like that. Yeah.
So this algorithm won't always give the right answer.
That's what we'll get to. Yeah. The greedy algorithm won't always give the right answer. Yeah. Okay, so the greedy algorithm is something that I just wrote down. It is choose coin of highest denomination smaller than x, and then recurse with x minus this cube. So this is actually a much simpler algorithm. Okay. So it is simpler, easy to implement. And so the question is this correct? Okay, so it's also natural, right? So you would want to do something like this, but is this always correct? So in the sense that, is the answer produced? So what do we have to show? So we have to show that for any d1 through dk and x, does greedy produce the minimum number of coins? So what do you guys think? So let me give you an example. Yeah.
Actually,
Do you have questions? It will or it won't? Can you give an example? Okay. Oh, so let me write it down. So, yeah, and what she's doing is the right thing. So you've got to give a counter example, right? So x is 36, and what are the denominations?
One is 30, and second is 18.
Oh.
And the third is 11.
Yeah. Okay, so this is a pretty clean example of why greedy can actually be really bad, right? So here if you do greedy, you actually would use some 7 or something like this number of coins. Okay, so you use 7 coins, while the optimum is just 2. Okay, so greedy. Optimum is just 2. So is this example clear to everyone? Yeah.
So if it was 30, 18 and 30, 18 and 4,
Okay.
then would greedy fail in this case?
And you still have 36? Yeah, so in this case, greedy won't even produce the, yeah, so that's the other issue. I didn't even mention that, is that sometimes greedy may not even, so greedy, at least the way we wrote it, need not even produce a feasible answer. So is the question clear? This is actually a great point. So he's saying that to start with this, greedy will just end up doing 30 and 4 and then it just gets stuck. Okay. So,
But with some combination like this, we may not be able to produce every value.
Right, so if you can, then you can solve subset sum. So that's what I was going to say. That there is, when we cover NP completeness, we'll look at this problem called subset sum. Okay, so in general, problems like this are actually NP hard. You give a bunch of values and you give some target x. You ask if there's a subset of these guys that add up to x. Okay, so this is what is called the subset sum problem, and this turns out to be NP hard. Okay, so the sense in which it's NP hard we will see when we come to the NP hardness section of this course. Okay, so, but yeah, that's a good point. Okay, but what we know is that greedy is not always the best. Okay, so this is fine, right? So in this case, turns out dynamic programming is probably the better way to go, because at least we know that it's always correct. So even though it seems inefficient, it's actually the right, it produces the right answer, whereas this simple greedy algorithm does not. Okay. So this is typical of greedy algorithms. Okay, so I will have a slide summarizing. So that greedy algorithms are simple, they work reasonably in applications, but they are not always correct. Okay, so this is something you've got to be wary of. So typically not correct. Okay, but typically they also give something useful. In this case, not necessarily, because like this solution can be arbitrarily bad, but we'll just see an example in which greedy is not optimal, but it's not that far from optimal. Okay. And in practice, usually greedy is like a first step. It gives a reasonable first step for various problems. Okay. And from there, you can try to improve the solution, you can do other things. Okay, so that's a quick summary. Okay. Alright, so this is the second example. So let's consider this problem. This is called the matching problem for those of you who have seen it. And the idea is, let's say you have a bunch of students, let's say the number is even, so that pairing is even possible. Okay. And your goal is to create project pairs. Okay. So you have 2n students, and there's a collection of acceptable partner pairs. So like every student has a bunch of people with whom he or she is okay partnering. Okay, so this graph could look relatively dense, it could look sparse and so on. Okay. We just don't have edges between people who are absolutely not fine working with one another. So that's this graph. And what is the goal? The goal is there a valid partnering for the entire class? So in this case, okay, I need another vertex. So yeah, so in this case, it is probably this, and this is a valid partnering because each of those is an edge, right? And so these two are okay working with each other, these two are okay working with each other, and so on. So, any question on the, yeah, let me just wait till you guys understand the problem. You can ask questions. Okay, so we have a collection of acceptable pairs and you have to pick like a subset of them, like a few of them, and they should cover the entire class. Okay, so that's another way of phrasing the same problem. Sorry? Oh. Okay, so this is called the matching problem, and it's a very well studied problem on graphs. Okay, so and the goal here is there a valid partnering for the entire class? Okay. So what would be a greedy algorithm for this? Like if you were to just come up with, suppose like a bunch of students came to you and said, oh, you are supposed to partner them. What would be an acceptable partner?
Rank all of the students, start assigning the pairs over their first, rank them arbitrarily, I should say.
Okay.
With their highest rank, whenever you get one that doesn't have an unmatched partner, boot the top of his list and move that person down to the next one. The ranking is just there to keep you from going into a second.
Yeah, so assume there's an ordering, so what you're saying is every person gets mapped to the first acceptable partner that is unmatched. So this is a perfectly reasonable thing. Okay, so this is what, okay, it's similar to what I wrote, but this is a perfectly natural way to do greedy as well. So start with a vertex, match it to the first order of vertices. So, if I is unmatched, match to first unmatched neighbor. Okay, and continue. Okay, if one exists. Yeah.
Wouldn't it be slightly better if the ordering were to be in the order of pickiness of a student? So first example.
Low degree vertices first. Yeah, so we'll come to these kind of heuristics later, but this is a good point. So if there's one person, for example, who has only one edge out, so if your goal is to partner everybody, like this is a particularly antisocial student, so maybe you want to just finish off, partner them first, and then continue with the rest, right? So that's a very reasonable thing. Okay, so it's you can first pre-order vertices increasing degree. So this is by degree, I mean degree in this graph that has all the acceptable pairs. Okay. So anything about this algorithm that's not clear? So I'm implicitly viewing this, the instance that we have as a graph, where you have a graph where every person, every student is a node. You have 2 n nodes. The edges just correspond to acceptable edges. That's how I'm modeling the problem, and I'm just trying to find first order and then match based on what he said. Okay, so this is a reasonable algorithm, right? So it's but is it optimal? Okay. So yeah, so if you do the sorting, I actually don't know an example off the top of my head, but this is a simple homework exercise for you. Okay, so if you play with it, you can come up with an example where this is not optimal. Okay, so, in fact, matching is one of the first very non-trivial algorithms. I mean, so especially for graph problems. So we'll see how even in like bipartite graphs, matching is actually kind of non-trivial to do. Okay, so these kind of simple heuristics just don't work. And it took a while and a lot of research for the first efficient matching algorithm to come out. Okay, so good. So any questions on the algorithm itself?
Does it always give a solution?
No, so that's the thing. So you could have a solution. I mean, you could have a situation in which the graph itself has a perfect matching or has a valid partnering, but this algorithm does not produce one. Okay. And in fact, it could stop like pretty badly midway through. Okay. But that's what I want to get at. Okay. So this is another algorithm I said. Then correctness. This is actually an exercise. Show that this is not. So let's not go about the correctness because with the sorting I actually don't know off the top of my head what our example is. But you can come up with one. Okay, but what I want to get at is this other question. So this is what is often true in greedy algorithms, okay, which is that even though what you produce is not really optimal, it's not that bad. Okay, so and sometimes you can actually prove that it's not that bad. Okay, so what I want to claim is that, so actually any guesses on how you might show a statement like this, like in this case, right? So suppose, meanwhile I'll charge this. But now you can think a little bit and so how would you show that the greedy algorithm is producing something meaningful or something that could be potentially useful? Can you come up with a statement that might be true? Yeah.
Maybe if there's another algorithm that does find the optimal but that's less efficient or something, you could show that and show the greedy version and then show the bound between them, like how close that it would come to the optimal.
Yeah, so and in what terms could we measure this, how close it could be? Okay, so what he said is a great point, right? So what he's saying is, so suppose there is a different algorithm, more complicated, what have you, and it produces a solution. Can you say that this simple solution is kind of, within some factor of this? Okay, and now the question is, what is the right parameter? What is the right metric to compare to such algorithm? So this is how you should think when you are thinking about these kind of problems. You should think, okay, what's a reasonable measure of how well this algorithm is doing? Okay. One measure could be, are you able to match the entire class or not? Okay. And that's okay, but it's not that informative because maybe you just missed two people, right? So your algorithm did a reasonable job, but there are just like a couple of leftovers. So any ideas on how you should quantify?
That could be a measure, how many were leftovers.
I realized I just gave the answer, but yeah.
One could be the size of subset that it could match, and building onto that would be how many corrections in this subset would lead to the actual optimum.
Yeah, so if there's one optimal matching, you can say that, but the second one. But what he said initially, so he gave actually two different metrics. One is you can look at the number of people who were actually matched. Okay. Just similar to what the other candidate was, which is the number of people who were not matched. Okay. So it's just the complements of one another. The other solution is you could say, oh, I produced a matching. There is some optimal matching, and what's the distance between these two? Okay, like how many flips do I have to do to get from one matching to the other? That turns out to be much more messy and much more involved, so we'll not get to that. But we'll go with the simpler version here of what you're saying, which is number of matched people. So let's do that. So we'll define an objective. So this is what is often, typically in optimization problems, we try to come up with an objective function, because having these kind of Boolean yes/no things, is there a perfect matching or not, is usually not a great way to proceed. Okay, so because there might be some leeway. Suppose you have the two students left out, you can convince them to work together or something like this, right? So that's what the objective function is for. This, in our case, is the number of students matched by that. Okay, so right, so and now my claim here is I want to make a claim of the following form. Okay, so I want to say that suppose I'll introduce a little bit more notation. So the objective value of greedy I'm going to write as obj of greedy. Okay, just so that I don't keep writing objective value of greedy. And an opt is the true optimum for the objective. So the true optimum is the best number of, the maximum number of students that can be matched by any algorithm. Okay, like you could look at an exponential time algorithm that tries every possible matching, and that's the optimum. Okay. Now I want to say that objective value of greedy is not much worse than the optimum, right? So what kind of a statement should I be proving? So I want to compare this with opt. Okay. And what do I write in between?
Minus opt is less than equal to sum.
Yeah, so you could write that. So it's this. Okay, we know that this is always negative, so this is less than equal to sum. So you could write a statement like this. And yeah, so this is totally fine, but in our case, we won't be able to get something on the right that's independent of the opt itself. Okay, so it will be tough to, I mean, it would be nice if you could get like 2 or something. Okay, I didn't know there's a door here. Anyway, so this kind of statement turns out to be a little bit harder to show, but what we will actually show is that objective value of greedy is at least a constant, in this case half of opt. So this is like saying if there is an optimum matching you found using some exponential running time algorithm that matches a total of k people, then this greedy algorithm matches at least k over 2b. So it's not great, it's a factor of 2 away, but it's such a simple algorithm, right? So that's often the thing with greedy algorithms, that they're just so simple that you're okay losing a little bit of factors, and hopefully in practice this might not be as bad as the half. So yeah. So is the statement clear of what we want to show? Okay. So this is the claim. Okay, so how would you prove such a statement? That the objective value of greedy is at least half the optimum?
So the optimum would always be like if n is even,
Okay.
then it's always true.
If n is what? N is, anyway, the number of nodes is 2n, so it's always even.
So if there indeed exists a matching for everyone, then the optimum will always give like n.
Will always be 2n or whatever, right? 2n is the total number of
2n.
nodes, okay.
But if it doesn't, then the optimum would probably give 2n minus 1.
That's fine. Well, I mean, optimum is whatever it is, right? But I want to say that greedy does something. Yeah.
Come up with the worst case example and show that it's half of 2n.
Great. But how do you say that that is the worst case? Okay, so yeah, so this actually works for a few problems. Okay, so there are problems in which you can say, oh, this is actually the worst possible ratio, and there the work is in showing why any other solution is not as good. I mean, is not as bad as this one. Okay, but there's often a much simpler argument for these kind of things. Where
Show that for any unmatched pair, there exists a unique match pair.
say that again. This is
Show
some
that
new
for
thing.
any unmatched pair, there exists a unique match pair. That'll give you 1/2.
Why is that?
Because so for any pair that should be matched in the optimal solution that is not, if you can map that to a pair that is matched, then that means that you have at least 1/2 matches.
So you're saying, okay, so let me try to, do that step by step. Okay, so you're saying, let's look at the optimal solution. So, okay, so this is bunch of matched pairs. Okay. Now you're saying that for any, and this, let's say, matches 2k vertices. So there are k such edges in the optimal solution. So this matches 2k vertices, right? Every edge has 2 vertices. Okay. Now you're saying, now you want to show that greedy at least matches k vertices. Okay. So that's what we want to show. All right. So now what are you saying? Are you saying that let's look at 2 of them?
Each matching that exists in the optimal does not exist in the greedy. Show that there must exist one in the greedy, a unique one, which is the symmetric component. But I think they can be done by showing that one of those 2 vertices has its own match and assign it to that. Does this make sense?
Yeah. So I'm going to formalize that. But but the idea is that suppose you had the optimal solution, which is like this, okay, and it's a bunch of edges. Let's say there's k edges, so there are 2k vertices there. What he wants to show is that somehow for every edge out here, he wants to say that greedy has matched at least one of these vertices. Okay, and that would result in a factor of 2 because there are k edges, and you are saying that for every edge, greedy had a matching to at least one of these guys. And they could be matched to one another, right? So you could have something like this, and then there's one person here who's matched to one person there. But that's fine because we are only counting the number of vertices that are matched. And yeah.
So if we match one vertex from each of the pairs to another one in the another pair, so
Mhm.
there are k vertices which are left because out of the 2 we are matching
Yes.
one to another.
Right. The k vertices that are left, but you might be unfortunate and maybe there's no edges between them. So then you're kind of stuck there. Yeah. Okay, so good. So we want to say that, so there's a subclaim that he's making, which is that for every edge in optimal matching, can come up with with a vertex that was matched by greedy. Can you see that? Okay. Yeah, sorry about the handwriting. It's kind of my hand is at the very tip of. Can you guys all read that? So the claim that he said, I just formalized it. It's just that take the optimal solution. For every edge in the optimal matching, you can come up with one vertex that was indeed matched by greedy. And note that this is how you're comparing greedy with the optimum in some direct way. Okay, and this is often the tricky part. You've got to figure out how to do this. So that's why, even though the claim may look innocuous, it's kind of intricate to actually come up with it. So this is the claim we want to show. Once you know the claim, this is actually somewhat easy to prove. So I'll see if you guys can come up with a proof for this. So the idea is, what we are saying is, take any edge in this optimal matching. I want to say that there is a vertex that greedy has matched, right? And the edge has two vertices, so it's natural to say, okay, can I say that one of them is actually matched by greedy? Yeah.
So since there are since there are 2k vertices, so in the greedy algorithm, if one of the vertex is not matched,
Yeah.
then there has to be another vertex in another pair which is also not matched, because there was an even number of vertices started.
So you're saying that if let me take some pair. Okay, this is a pair in greedy. You're saying if this guy was not matched,
Yeah, then in some other pair another vertex is also not matched. Which can
now
be
you're
matched.
talking about the greedy element, right?
Yeah, in the greedy.
So why should that be? I mean, there could be a third there could be a vertex that goes outside. And maybe this guy was matched to this. Remember, the way we are assuming things, we're not assuming optimum covers everything. I mean, if not, you're right. I mean, if optimum covers everything, then there is somebody else. But we're not assuming. There could be like a vertex that's not in any pair in the optimum. And maybe this guy was just unlucky match to that to start with. But that's a good line of thinking, yeah.
So if we assume none of these nodes has been matched before, then the greedy algorithm should choose one of them or both of them to be matched.
Okay, so that's actually the right answer. So what he said is, so suppose this claim were not true. So what does that mean? So we're saying that at the end of executing greedy, you had some pair out here such that neither of these two was matched. Okay. But that couldn't have happened because what does greedy do? It goes through each of the vertices, tries to match it to somebody or the other. Okay. And as long as they have a neighbor who is not matched. And in this case, suppose I get to one of these guys. Okay. Suppose I get to this top node, and so greedy would have gone through this node. And at that point, it would have looked at all its neighbors to see if they were matched or not. And one of its neighbors is actually this other vertex. So it should have found an unmatched neighbor. Okay. So there's no way greedy could not have matched both these vertices. Could just be that greedy matched them to somebody who is totally outside this set and so on. But that doesn't matter. We are only in the business of counting the number of nodes that were matched. So that's the idea. That look at greedy, the execution of greedy. And that immediately implies this, that if there were some there, then during the execution this must have been matched to that. Or it doesn't have to be matched to this guy, but we know at least that there is some unmatched name. And I could have matched to that name. Okay, so questions on this? Pause for a little bit because and now you guys should now realize that once we prove this we are done, because so as you were saying, this is where the factor of 2 comes in. Okay, so we had k different edges. For every edge we are producing one node that was matched by greedy. So ultimately we are only saying that there are at least k nodes that were matched by greedy. So opt of greedy, the objective value of greedy is at least k, and opt we assume was 2k, so that's why there's a factor of 2. Yeah, so questions on this? Yeah, so these kind of arguments, I mean, it's important to pay attention to what we are doing here, because in some sense you want to compare what this algorithm greedy is doing with what the optimum is doing. And so what we are saying is you look at the optimal solution and then you say that this algorithm has to at least have a decent chunk of the, has to have a value that's at least a reasonable factor of this, right? So it's interesting to kind of make sure you understand how we are using this algorithm itself in the proof. In this case, the way we are using it is to prove this subclaim that if not, then during the execution when you looked at this vertex, you would have found this other one. So that's how we are using the algorithm itself in the proof. So let's continue, but you guys should look back at this proof, try to convince yourself. Best way to do these kind of things is try to go back and prove it to yourself that, okay, why does this give a two-factor approximation? And then you'll see that some intricacies involved. That's usually a good idea. Okay. Slide for the proof. Okay, so again, so this is like a quick summary of greedy. Okay, so typically greedy algorithms go by this common mantra. Okay, so that you always have a present state, which is typically a solution until this point. You always pick one option that improves your state. Okay, and usually you pick the best option at the present state. And sometimes you can do some pre-processing and then things work out. The other thing about greedy is it almost never works. Okay, so for most problems, greedy could be pretty far away from optimal. Okay, but it's still a very natural paradigm, that's why we study it. And there are also problems in which it actually does work. We'll see an example of that shortly. And but typically it provides insight, okay, and it also suggests other methods. Because when you see a problem for the first time, typically what you should think of is, oh, is there a simple greedy algorithm for this that I can use? And often it doesn't work. In the process of figuring out why it doesn't work, you might come up with a better way of solving it. Okay, so that's something, that's why I say it provides insight. And sometimes it almost works. Okay, so we've seen one example of this, the matching one, where it's two-factor away, so it kind of works. So, and it's very easy to implement. So if you see the other algorithm for matching, you'll see why this is probably what you might want to do if your application is not very serious. Okay, so any questions roughly about greedy? So I guess the tricky part is this, right? How you reason about greedy algorithms. And yeah, so I just wanted to illustrate a couple of methods. So one we've seen now. So this is an example of, yeah. So we'll see two ideas, roughly speaking, to reason about how you actually show greedy could be optimal. So So there are some problems for which greedy is optimal. And yeah, we'll see these kind of things. But typically, it's very problem specific. So the way you argue about an algorithm depends on the algorithm itself. So there's no single answer to this. Okay, so I wanted to give a different example, and this is of scheduling jobs. Okay, so suppose you have a machine, you have a collection of jobs. So scheduling is one of the classic problems studied in algorithms. So you have, sometimes you have different machines, but in this case we just have a single machine. Okay, so you have a single machine. Okay, you are given a collection of jobs. Okay, and these are jobs 1 through n, and job I has processing time pi. Okay, think of it as the length of a job. You want to find a schedule which is an order in which to do these jobs. So it's ordering in which to perform these jobs. Okay. So that you minimize the sum of the completion time. So what is a completion time? So let's take a very simple example. So let's have job 1 of, so let's write down jobs and processing time. So let's call this A, and processing time of for B is processing time 5. Okay. And what are we saying? We want so we want to schedule them. Okay, what does that mean? It's just an ordering in which to complete. So you have a machine, and it wants to do them in a particular order. Okay, so at every time step you can only you can only be running one job. So, alright. So it could do A, B, C in that order. So in this case, what is the completion time for A? Let's say you start at t equals 0. Yeah, completion time for A are, so if I look at now job and completion time. So for job A it is 4. What's it for B? 9, because you do B after A, and C is 12. Yes, I just wanted to run a simple example to see what the objective is. And the objective value in our case is the sum of these completion times. Okay. Now our goal is to schedule these jobs in such a way that you minimize the completion time. So when would you want to solve a problem like this? Suppose you have a bunch of clients, and for every person you have to pay some penalty based on when you actually finish their job. And your goal is to minimize the total amount of payoff you make to all the people put together. So then you might want to do things like this. That's one situation where this particular problem arises. So, right, so for this problem, what would be a better schedule than ABC? Somebody said, okay, I've heard all possible permutations. Okay, so let's look at CAB. Okay, so here what's the completion time for A? Okay, so it's 7. For B? So 12 you can avoid. And what's it for C? Okay, and as you can see, this is a little bit better than the previous one because 7 plus 3 is bigger than 9 plus, is smaller than 9 plus 4. So this is what you observed. And how did you guys come up with this ordering? hopefully none of you said I checked all possible. Okay, so
Which comes fast?
yeah, so in this case, there is some intuitive notion that I need to get jobs done as quickly as possible, right? Because our goal is to minimize this completion time. So a reasonable heuristic seems to be that sort jobs in increasing order of completion, increasing order of processing time. Of processing time. And just execute them in that order. Okay, so in this case, C was, the order is C, A, B, so that's the order which you execute. Okay, so this is a simple greedy algorithm. And you can think of it as an incremental algorithm, because you always say, oh, do the smallest job, do the next smallest job among the jobs that are left, and so on. Okay, so you can think of greedy algorithms typically as incremental ones. Alright, so is this going to give an optimal solution?
Yes.
Okay, so this is, so problems like these are some nice exceptions in which greedy actually works. Okay, so here you can actually show that the answer is yes. And so now the question is why? Okay, so how would you show that there is no better schedule? Yeah.
So if you assume that there is a different, the contradiction,
Okay.
you assume that there is
Yeah.
an alternate
So
property.
right. So this is one thing. Okay. So about reasoning about greedy algorithms, a typical way that works is you say that, oh, suppose greedy algorithm is not the best possible. Take any other schedule or take the optimal one. Try to show that it can't be actually bigger than greedy. Okay, so let's go on. Okay, so consider the optimal schedule. I'm also going to make life simpler by saying that suppose the greedy schedule is job 1 followed by job 2 followed by job n. So I've just sorted the jobs in increasing order process, and I want to show that then this ordering is actually the right one. So is that clear? So that's just saying, suppose the jobs were already sorted in increasing order. Otherwise you just permute them and figure out what the right one. Alright, so now you're saying consider the optimal schedule, and suppose it's not 1 through n, then what's the argument?
Then you have to show that it's going to be, if it's, let's say, a higher time taking task is before something which takes, so it's not sorted basically. So if we swap them, it will give a lower completion time.
Okay, so what he's saying is greedy schedule has jobs listed out in this order. Okay, so now let's look at the optimal schedule, and let it be something like I1, I2 to In. Okay, and you're saying take any pair here where this one is, take any pair Ix and Iy such that x is less than y and Ix is bigger than I1. That's what you're saying. Right? So x is less than y means x comes before y. This is the xth position. This is the yth position. Okay. And this is I sub x, this is I sub y. It's looking at two indices where I sub x is bigger than I sub y. And if I sub x is always less than I sub y, then it's sorted, because that means that consecutive ones are always increasing. So, as if this sequence is not exactly the same as 1 through n, then there have to exist two things that are out of order. So take those out of order guys, you're saying just swap them. Okay, so swap them. Now you're saying the claim is schedule only improves, right? So the sum of completion times only improves after swapping. I'm just periodically saving because few classes ago we had this problem. So, alright, so why is this enough? I mean, suppose you show this. So is this enough to say that we've actually proved optimality? So, any reason? I thought I saw you nodding.
Oh, yeah. Well, it's a contradiction because they want to do the optimal schedule.
Yeah. So if it's if you can improve it, then it's not optimal, right? So that's why if you could show that swapping improves the solution, then you're done. Okay, so this is often how you show this. All right. So that's why proving this claim is actually enough for what we want to show. Now, how would you prove this claim? So we've got to now analyze the sum of completion times. Right. So how does the sum of completion times vary?
For any jump between the x position and the y position, we are adding ix now instead.
Okay, and that's good for you.
Yeah, so like we are now adding the smaller value between ix and i.
Okay, and what about the others?
The others will remain the same.
Okay. So is this argument clear? So she just said, what she said is, let's look at these x and y positions and swap them. The effect of the swap is basically that the completion times of everybody before x will remain exactly the same. Everyone between x and y minus 1, instead of adding the processing time of x, we will now add the processing time of y. And by assumption, processing time of y was actually less than the processing time of y. So all those guys have a smaller contribution to this sum of completion times. Okay? And what about the ones after? The ones after remain exactly the same. Okay? Because no matter what, you're just adding everything before. So, and that's basically the argument. Okay, so that's what I will write. So, just so that we have a. Oh, sorry. So it's safer to write down. So the proof is basically that look at the objective values. values before and after swap. I'm glad I saved it. So, or rather the objective value after swapping. And so the objective values are always sum of completion time, right? So your original ordering was I1, I2 up to IN. By the way, I think I have a mild, yeah. So up to IN. And taking two guys that were out here and swapping them. Okay. So there were three observations. Okay, so one is that the completion time this is Ix, this is I, of jobs I1 through Ix minus 1 remain the same. The other was completion times of jobs Ix through Iy minus 1 only decrease. The third was Iy through In remain the same. So, and this is it, right? So with these three claims we are done, because basically we are saying that these guys only decrease, so the overall it should only decrease. And so of these two are trivial, because this is just from the definition of completion time. The order is basically the same, just two of the things got reversed. And so yeah, by the definition of completion time, anyone after this will have the exact same completion time as before. And same is true for anyone before this. And this one is true because initially the processing times were sorted. Okay, so initially we had Pix is bigger than Piy, and yeah. So I'm not going to be this formal about this. Okay, so this is fine to just say that now you have a smaller contribution to the completion time. So I think sometimes writing too many letters just complicates the intuition. So you should just not do it. Okay. So all right. So any questions on why this works? Yeah.
So can you also just prove this by kind of expanding out the sum in terms of the i's and then combining the like terms, so you get the sum is equal to n times I1 plus n minus 1 times I2, and then proving that to minimize that sum, you need the one that has the highest weight, which would be I1, would need to be the lowest.
Yeah.
The one that has the second highest weight would need to be the next lowest.
Yeah.
Could you also do that? Or?
Yes, that's actually a very clean way of doing it. Okay, so let me just write it out so that everybody understands. So what he's saying is, it's a nice way of showing this. So suppose you have some ordering, Okay, so let's consider the ordering this I1, I2 up to IN. And what is the sum of weighted completion times in this case? Okay, so the objective value is basically PI1 plus PI1 plus PI2 plus PI1 plus PI2 plus PI3. And this, if you expand it out, is basically n times PI1 plus n minus 1 times PI2 plus so on up to 2 times PI n minus 1 plus PI. So do you, any questions in this? I just combined like terms as he said. Okay, so the I1 appeared n times, this guy appeared minus 1 times. And now if I have to, yeah, so now what do I have, right? So I have a sum where I have n times the processing time of the first one plus n minus 1 times the processing time of the job I do next, okay, plus n minus 2 times the job I do the third step, plus so on. And if you've got to minimize this sum, you have to pair up the largest value with the smallest one, right? So that's how you're going to minimize it. So that's another very clean way of doing it. So yeah, so this is actually a perfectly fine way of doing the same thing. The reason I didn't do it is because this is kind of specific to this problem. I wanted to kind of also have this general thing that the way we argued here, just consider any other solution and try to show that it can be improved, is a more general technique. Okay, so very often problems don't decompose so cleanly, so that's why we did it. So this is a great solution. So yeah, any other questions? Okay, so if not, I will end here. So, but tomorrow I will also send a link to Jeff Erickson's notes. It has a couple of other examples of greedy algorithms, and I'll also have a link to some pages in the textbook where you might want to read a few nice greedy algorithms. So these are more like optional readings. I mean, they'll just give you more examples of greedy algorithms that you can play with. So we'll also see maybe one more next time, and we'll also look at local search next time. Okay, but the summary slide on greedy is what you should remember. Just that usually it doesn't work, but it gives a reasonable answer, and there's some cases in which it actually gives the right answer. So when we look more concretely at spanning trees, that's another place where greedy algorithms actually give the right answer.